When calculating voltage drop for an outlet branch circuit, especially in residential applications, you typically want to use the actual connected load. That means determining the amperage that the devices plugged into the outlets will draw under normal operation. If the actual connected load isn't known, the National Electrical Code, or NEC, provides guidelines that can be used to estimate the load. Specifically, NEC Table 210.21 B2 lists values for estimating total wattage when the connected load is not known. For a 110-volt circuit, this table gives a value of 180 volt amps per outlet. However, it's important to understand that using these values is not mandatory. They serve as a guide when the actual load is uncertain. Now, if an electrical inspector is checking the circuit, they often have a meter that allows them to load the branch circuit to different amperage values. They might have the option of loading it to 12 amps, 15 amps, or 20 amps. Each of these values serves a different purpose during the inspection. The 12 amps load value represents the minimum load required to trip a 20 amps breaker. This value is used to verify that the breaker will indeed trip under overload conditions, ensuring safety. The 15 amps load value is a common load used for general testing. It provides a reasonable load for the circuit to handle during the inspection process without causing any issues. The 20 amps load value is the maximum load that the breaker should allow without tripping. This value confirms that the breaker can handle its rated load under normal operating conditions. In most residential scenarios, using the actual connected load is generally recommended when calculating voltage drop. If the connected load remains unknown, you can refer to NEC Table 210.21 B2 values as a guide. When an inspector is testing the circuit, they will likely choose to load the circuit to one of the values mentioned earlier. They are more than likely to use 12 amps to ensure that the breaker does not trip unexpectedly during the inspection, allowing them to thoroughly evaluate the circuit's performance. To elaborate further on voltage drop calculations, understanding Ohm's law is fundamental. Ohm's law states that voltage drop is equal to the current flowing through a conductor multiplied by the resistance of that conductor. The formula is voltage drop equals current times resistance. In electrical systems, conductors possess inherent resistance, and as current flows through them, a voltage drop occurs. The amount of voltage drop permissible is regulated by electrical codes like the NEC to maintain optimal performance and prevent damage to equipment. The NEC provides guidelines on the maximum allowable voltage drop for branch circuits and feeders. These limits are typically expressed as a percentage of the source voltage. For example, the NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate voltage drop accurately, several factors must be considered, including the conductor's length, size, and material, as well as the current flowing through it. Longer conductors have higher resistance, which leads to greater voltage drop. Similarly, smaller conductors have higher resistance compared to larger conductors, resulting in increased voltage drop. Copper and aluminum are commonly used conductor materials, with copper generally having lower resistance than aluminum. When determining the appropriate conductor size for a circuit, voltage drop calculations play a crucial role. The goal is to select a conductor size that minimizes voltage drop while remaining within the NEC allowable limits. If the calculated voltage drop exceeds the maximum allowable limit, the conductor size must be increased to reduce resistance and lower voltage drop. In addition to conductor size, other factors can influence voltage drop in electrical systems. These factors include the type of load connected to the circuit, the power factor of the load, and the presence of harmonics. Inductive loads, such as motors and transformers, tend to have lower power factors, which can increase voltage drop. Harmonics, which are non-sinusoidal waveforms, can also contribute to voltage drop in electrical systems. To mitigate voltage drop in electrical systems, several strategies can be employed. These strategies include using larger conductors, shortening conductor lengths, improving power factor, and reducing harmonic distortion. By implementing these measures, voltage drop can be minimized, ensuring efficient and reliable operation of electrical equipment. In summary, calculating voltage drop is essential for designing and maintaining electrical systems. By understanding the factors that influence voltage drop and implementing appropriate mitigation strategies, engineers and electricians can ensure that electrical equipment operates safely and efficiently. Regarding the NEC Table 210.21 (V2), it is imperative to note the specific applications for which it is intended. This table provides guidelines for the minimum ampacity of conductors and the overcurrent protection devices required for various types of electrical equipment. The values listed in the table are based on the continuous load current of the equipment, as well as any non-continuous loads that may be present. It is crucial to consult the NEC and other relevant standards to ensure compliance with all applicable requirements when selecting conductors and overcurrent protection devices. Now let's talk more about the inspector's role in assessing voltage drop and circuit integrity. When an electrical inspector evaluates a branch circuit, their primary concern is ensuring that the circuit meets safety standards and functions as intended. To assess the circuit's performance under load, the inspector may use a circuit analyzer or a similar testing device. This device allows the inspector to simulate various load conditions and measure parameters such as voltage, current, and voltage drop. During the inspection, the inspector may choose to load the circuit to different amperage values to evaluate its performance under varying load conditions. As mentioned earlier, the inspector may use values such as 12 amps, 15 amps, or 20 amps, depending on the specific test being performed. By measuring the voltage drop at different load levels, the inspector can determine whether the circuit meets the NEC voltage drop requirements. If the measured voltage drop exceeds the allowable limits, the inspector may require corrective action to be taken, such as increasing the conductor size or reducing the load in the circuit. In addition to voltage drop testing, the inspector may also perform other tests to assess the circuit's integrity. These tests may include checking for proper grounding, verifying the correct polarity of receptacles, and testing the operation of ground fault circuit interrupters, or GFCIs. By conducting thorough inspections, electrical inspectors play a vital role in ensuring the safety and reliability of electrical systems. It's important to remember that voltage drop is not the only factor to consider when designing and installing electrical circuits. Other factors, such as conductor ampacity, overcurrent protection, and grounding, must also be taken into account to ensure a safe and reliable electrical system. In addition to the information provided in the NEC, there are also various resources available to help engineers and electricians calculate voltage drop. These resources include online calculators, software programs, and engineering handbooks. By utilizing these tools, it is possible to accurately calculate voltage drop and select the appropriate conductor size for a given application. Ultimately, the goal of voltage drop calculations is to ensure that electrical equipment receives the proper voltage to operate efficiently and reliably. By minimizing voltage drop, equipment performance can be optimized, and the risk of equipment failure can be reduced. Remember, understanding and addressing voltage drop is an integral part of electrical system design and maintenance. While the NEC provides guidelines and recommendations, the specific requirements may vary depending on local codes and regulations. Therefore, it is essential to consult with qualified electrical professionals and adhere to all applicable standards when working with electrical systems. Now let's delve deeper into the implications of excessive voltage drop on electrical equipment. When voltage drop exceeds the allowable limits, it can have several adverse effects on the performance and longevity of electrical devices. One of the primary consequences of excessive voltage drop is reduced equipment efficiency. Electrical devices are designed to operate within a specific voltage range, and when the voltage drops below this range, their performance can suffer. For example, motors may run slower, lights may dim, and heating elements may produce less heat. This reduction in efficiency can lead to increased energy consumption and higher operating costs. In addition to reduced efficiency, excessive voltage drop can also cause equipment to overheat. When the voltage drops, electrical devices draw more current to compensate for the reduced voltage. This increased current flow can cause components within the device to overheat, leading to premature failure. Overheating can damage insulation, windings, and other critical components, resulting in costly repairs or replacements. Furthermore, excessive voltage drop can affect the reliability of electrical systems. When equipment is subjected to voltage fluctuations, it can become more prone to malfunctions and breakdowns. Voltage drops can also cause sensitive electronic equipment to malfunction or shut down unexpectedly. These disruptions can lead to lost productivity, data loss, and other undesirable consequences. To prevent these issues, it is essential to maintain voltage drop within acceptable limits. This can be achieved by selecting appropriate conductor sizes, minimizing conductor lengths, and ensuring proper load distribution. Regular inspections and voltage measurements can help identify potential voltage drop problems before they escalate. Now let's explore some practical examples of voltage drop calculations in different scenarios. Consider a branch circuit supplying power to a string of LED lights in a residential setting. The LED lights have a total load of 100 watts and are connected to a 120 volt circuit. The circuit is wired with 14 American wire gauge copper conductors, and the distance from the circuit breaker to the lights is 50 feet. To calculate the voltage drop, we need to determine the resistance of the conductors. According to the NEC, the resistance of 14 American wire gauge copper conductors is approximately 2.525 ohms per 1000 feet. Therefore, the total resistance of the 50 feet conductor is 0.12625 ohms. Next, we need to calculate the current flowing through the circuit. Using Ohm's law, we can determine that the current is equal to the power divided by the voltage, which is 0.833 amps. Finally, we can calculate the voltage drop by multiplying the current by the resistance, which gives us a voltage drop of 0.105 volts. This voltage drop is well within the allowable limits for a branch circuit. Now let's consider a different scenario involving a feeder supplying power to a large air conditioning unit in a commercial building. The air conditioning unit has a load of 20 kilowatts and is connected to a 480 volts three-phase circuit. The circuit is wired with 2/0 American wire gauge aluminum conductors, and the distance from the service entrance to the air conditioning unit is 200 feet. To calculate the voltage drop, we need to determine the resistance of the conductors. According to the NEC, the resistance of 2/0 American wire gauge aluminum conductors is approximately 0.294 ohms per 1000 feet. Since this is a three-phase circuit, we need to multiply the resistance by a factor of 0.866 to account for the phase-to-phase voltage. Therefore, the total resistance of the 200 feet conductor is 0.51 ohms. Next, we need to calculate the current flowing through the circuit. Using the formula for three-phase power, we can determine that the current is equal to the power divided by the square root of 3 times the voltage, which is 24.6 amps. Finally, we can calculate the voltage drop by multiplying the current by the resistance, which gives us a voltage drop of 1.22 volts. This voltage drop is also within the allowable limits for a feeder. These examples illustrate how voltage drop calculations can be applied in different situations to ensure that electrical equipment receives the proper voltage. By understanding the principles of voltage drop and utilizing appropriate calculation methods, engineers and electricians can design and maintain safe and efficient electrical systems. In addition to the factors discussed so far, it is important to consider the impact of temperature on conductor resistance. Conductor resistance increases with temperature, which can lead to higher voltage drop. The NEC provides temperature correction factors that can be used to adjust conductor ampacity based on ambient temperature. These factors should be taken into account when calculating voltage drop, especially in high temperature environments. Furthermore, it is essential to consider the impact of harmonics on voltage drop. Harmonics are non-sinusoidal waveforms that can distort the voltage and current in electrical systems. Harmonics can increase voltage drop and cause equipment to overheat. Harmonic filters can be used to mitigate the effects of harmonics and reduce voltage drop. In conclusion, voltage drop is a critical consideration in electrical system design and maintenance. By understanding the factors that influence voltage drop and implementing appropriate mitigation strategies, engineers and electricians can ensure that electrical equipment operates safely, efficiently, and reliably.